Okay. Okay, so I think, let me see here. I think okay, I think I'm live now. So let me proceed now to a discussion of chapter 2. As I said before, chapter 2 deals with, how do I get rid of this thing? I don't want to see myself. Okay, so in chapter 2, we'll be dealing with atoms, molecules, and ions. And as promised, I'm going to go through this rather quickly because, again, this is something that you should have met before in your introductory course, introductory chemistry course. So the first thing we're going to discuss here is what is known as the laws of chemical combination, all right? And the first law we're going to talk about is the law of conservation of mass. And basically what that law says is that the total mass remains constant during a chemical reaction. So in other words, in any chemical reaction, the total mass of the reactants would be equal to the total mass of the products, all right? So basically what this is saying is that the mass of all the materials involved in a reaction is conserved. So that's the law of conservation of mass. And that's important, as you're going to see later on, when it comes to doing certain calculations, right? You can basically exploit this law, or there are certain principles based on this law, which allows you to, for example, calculate the amount of products of a reaction given a certain amount of reactants. Okay, the next law that we're going to talk about is the law of definite proportions. And basically, this law says that all samples of a compound have the same composition, or another way of stating it is that all samples are have the same proportions by mass of the elements that are present. All right. So here's an example of that law being demonstrated. Okay, I have the wrong thing here. So this compound, and I'll be honest with you, I don't remember the name of this compound. I think it's copper hydrogen carbonate. In any case, this compound has 57.48% copper, 5.43% carbon, 0.91% hydrogen, and 36.18% oxygen, right? And that is true for that substance, regardless of where you get that substance from, right? So for any pure substance, the proportion mass-wise, percentage-wise by mass, would be the same. If I were to use a simple example, hold on 1 minute. Let me see if I can find a connection cord here. I hope this works. Let me see here. Okay, let's try this. Let's see if this works. I've been having problems with the writing. Okay, this works. Very good. All right. So what I'm going to do is, hold on. Let me go here. Oh, so this is basic copper carbonate. Okay. Let me get out of this here and go to a new, let me insert a new slide because I want to give another example of this particular law of definite proportion. So in the case of a simple example like water, we all know what the formula for water is. The formula for water is H2O. And if you were to break down any sample of, water, you'll see that the percentage of oxygen is about 89%, and the percentage of hydrogen is 11% approximately, all right? So these are the numbers representing the percentages of each of those elements that make up water, right? And those percentages are fixed. So it doesn't matter where you get the water from. It doesn't matter if you get the water from rain or if you get it from, from a river or from, any source. It doesn't matter. as long as it is water, then the percentages will be as stated here. 89% approximately will be oxygen, and the rest would be hydrogen. All right, and that is true for any pure substance. The percentages of the different elements will be fixed. Okay, so let me go to the next slide. So next slide is an example. It says the mass ratio of oxygen to magnesium in the compound magnesium oxide is 0.6583 to 1. So the question is, what mass of magnesium oxide will form when 2.00 grams of magnesium is completely converted to magnesium oxide by burning in pure oxygen gas? So basically, we know that the ratio of magnesium, of oxygen to magnesium, is given right here. That's information given, all right? And you're given the mass of magnesium that you're starting off with. So you can find out the mass of oxygen by simply taking this mass here, 2.000 grams, and multiply it by a conversion factor, which represents the ratio between the magnesium and the oxygen. So this is 2.00 grams of magnesium. And we know that for every 1 gram of magnesium, there is 0.6583 grams of oxygen. Let me take all these. Okay, let me redo this here. So this is magnesium and 0.6583 grams of oxygen, right? So let me get my calculator and work this out. So it's going to be 2.000 times 0.6583. And according to my calculation, this works out to be equal to 1.31, how many sig figs? 4 sig figs. So this should be 7 grams of oxygen, all right? So basically, the mass of magnesium oxide that is formed would be equal to the original mass of magnesium, which is 2.000 grams, plus 1.317 grams of the oxygen. So plus 2. So the final answer is going to be 3.317 grams. So this will be the final answer, which would be the mass of the magnesium oxide that is formed. All right. Okay, any questions about this example? Any questions?
No questions.
Okay, all right. So let's continue. Another law that you need to be aware of is what is known as the law of multiple proportion. Now, this one, the way it's worded is a bit lengthy, a bit wordy. It says when 2 or more different compounds of the same 2 elements are compared, the masses of one element that combine with a fixed mass of the second element are in the ratio of small whole numbers. So what that means is that if you have 2 compounds formed from the same element and you keep the mass of one of them fixed, then the masses of the other elements would exist in whole number ratios when you compare their masses between the different compounds. So let me explain that by using this example, the example of comparing carbon monoxide to carbon dioxide, right? So this is a formula for carbon monoxide, CO, and this is a formula for carbon dioxide, CO2. So let's say that you weigh a certain amount of each of these gases such that 3 grams of carbon would be present in whatever that sample is in each case, right? And then what you compare the masses of the oxygen that is present in that same sample. And what you'll find is that there is a whole number ratio between the masses of the oxygens, provided, whoops, sorry about that, provided that the mass of the carbon is fixed in both cases, is the same in both cases, right? And as you can see clearly, in this case, there's a 2-to-1 ratio as far as the masses of oxygens are concerned, right? Which corresponds to what you observe in the formula, because in the formula for carbon monoxide and carbon dioxide, you see that for every one carbon atom, in the case of carbon monoxide, you have one oxygen atom. In the case of carbon dioxide, you have two oxygen atoms. So therefore, when you compare the ratio of oxygens between these two compounds for the same amount of carbon, it's going to be a 2-to-1 ratio. And that is basically what is observed when you compare the masses, right? So the ratio of the oxygen to carbon in carbon dioxide is exactly twice the ratio in the case of carbon monoxide, all right? So that's basically what the law of multiple proportions is saying. Okay, so another example demonstrating this law is in the case of a situation where you have 28 grams of nitrogen reacting with oxygen to form 4 different oxides. So there's one particular oxide where 28 grams of nitrogen will react with 16 grams of oxygen to form one compound. In the case of another oxide, the same mass of nitrogen will react with 48 grams of oxygen to form compound 2. And then you have another oxide where the same mass of the same mass of nitrogen will react with 64 grams of oxygen to form compound 3. And then finally, same mass of nitrogen will react with 80 grams of oxygen to form the 4th compound. And if you look carefully at these numbers here, you see that there's a ratio, 16 to 48 to 64 to 80. If you express that in terms of whole numbers, what you can do is divide right through by 16. So if you divide right through by 16, the ratio becomes, hold on 1 minute. If you divide right through by 16, the ratio becomes 1 to, hold on, 48 divided by 16, that would be 3, I think. Right, that would be 3. And then this would be, if I'm not mistaken, this would be 4. And if I'm not mistaken, this would be 5. So there's a 1 to 3 to 4 to 5 ratio between the masses of the oxygens for samples of the different compounds where the mass of nitrogen is fixed at 28 grams. And the compounds actually would be these compounds right here, right? Let me show you here. So the compounds, I'm sorry, hold on 1 minute. So the compounds are listed down here, right? You have these compounds here. And if you look at the number of molecules of nitrogen, or the number of atoms of nitrogen per molecule, it's fixed in all cases, but the ratio of the oxygens would basically follow the same ratio as we have up here, right? This would be 1 to 3 to 4 to 5. All right, so basically that, again, is another demonstration of the law of multiple proportions. Okay, the next thing we're going to talk about here is Dalton's atomic theory. And in this theory, which was proposed by Dalton in 1803, he basically looked at all available knowledge concerning how substances behave, the type of reactions they undergo, and so on. And he also looked at the different laws that we just discussed, the law of the conservation of mass, the law of definite proportions, and the law of multiple proportions, right? So he combined all these, he considered all these laws, and he came up with an explanation, a theory, to explain these laws. And the theory is now known as Dalton's atomic theory. So we're going to look at the main assumptions of this theory, the first of which is that matter is composed of atoms. And these atoms are very small, very tiny, indivisible particles. Now, before I move on to the other assumptions, let me just say that we now know that this particular statement, that the atoms are indivisible, right? We now know that that is not true, right? Because we now know, and this was discovered more than a century after Dalton came up with this theory, we now know that actually the atoms are made up of smaller, more fundamental particles, namely the protons, electrons, and the neutrons. And we're going to discuss that later on in this course. In fact, you should have encountered those particles in your introductory chemistry course, right? So that's one flaw in his theory, which is perfectly understandable because back then, you know, not much was known about the nature of the atoms. They did not have the technology to probe into atoms to see exactly what these fundamental particles are. So back then, the assumption is that these particles are indivisible. All right, so that's the first assumption. The next assumption is that all atoms of a given element are the same. So basically what this assumption is saying is that if you could look at two atoms of the same element, let's say you have two sodium atoms, then they will look exactly the same. They won't be different in any way in terms of, you know, their appearance, all right? So that's basically what that assumption is saying. The third assumption is that if you compare atoms of different elements to each other, then they will look different, all right? And then the fourth assumption is that the formation of compounds come about as a result of atoms of different elements combining in fixed proportions. So we saw the example of water, which is made up of two elements, hydrogen and oxygen, in fixed proportions. In terms of the number of atoms, for every molecule, there are two atoms of hydrogen and one atom of oxygen. And then the fifth assumption is that a chemical reaction involves rearrangement of atoms. Atoms are created, destroyed. I'm sorry, no atoms are created or destroyed or broken apart, all right? And this particular assumption is what is used to explain the law of conservation of mass, right? Because if you recall, we say that the law of conservation of mass basically says that matter is not created nor destroyed in a chemical reaction, or the matter is conserved. The mass of the products would be equal to the mass of the reactants. And the reason why that is true is because of this particular assumption of the Dalton's atomic theory, because basically matter is not destroyed or created in a chemical reaction, and that's because the atoms themselves are not destroyed or created in a chemical reaction, all right? The only difference between the reactants and products is basically how the atoms are arranged, how the atoms are bonded to each other or combined with each other. Okay, so just to give you a demonstration, a pictorial demonstration of the Dalton's atomic theory as it applies to the conservation of mass and definite proportions. So here we have some models representing fluorine molecules and hydrogen molecules. And in this particular situation, we have 3 fluorine molecules and 2 hydrogen molecules. Now, the equation for this reaction is actually this right here, F2 plus H2 to give 2HF, all right? So that's a reaction that we're looking at here, right? So basically, for every molecule of hydrogen that reacts with a molecule of fluorine, will produce 2 molecules of hydrogen fluoride. Now, in this situation that we have up here, we have 3 fluorine molecules here, and we have 2 hydrogen molecules here. So what's going to happen is that this hydrogen molecule will react with one of the 3 fluorine molecules here, and this hydrogen molecule will react with another of the fluorine molecules here. So the result will be the formation of these 4 hydrogen fluoride molecules, right? And that means that one of these fluorine molecules will be left over, all right? So basically, if you count all the atoms of the different elements before and after the reaction, you'll see that the number of atoms of each element will be the same before and after. So therefore, the mass will be conserved, all right? And you'll notice that in the case of the hydrogen fluoride that is formed, it's a 1-to-1 ratio between the atoms that make up the molecule, right? So as stated down here, hydrogen fluoride always has 1 atom of hydrogen combined with 1 atom of fluorine. So therefore, if you look at the percentage by mass of each element in the hydrogen fluoride molecule, is going to be 1-to-19. If you look at it in terms of the ratio, 1 gram of hydrogen for every 19 grams of fluorine, all right? So that basically is a simple demonstration of the conservation of mass and the definite proportions law. Okay, let's move on to a discussion of the subatomic particles, which we talked about earlier. So by now, you should know that in any atom, you have three fundamental particles. You have the protons and neutrons and electrons. The protons and the neutrons are located in the nucleus of the atom, which is at the center of the atom. And then you have the electrons, which are dispersed around the nucleus. Now, later on, I think in chapter, if I'm not mistaken, chapter 7 or 8, we'll talk about how these particles were discovered. But for now, we're just going to talk about the fundamental nature of these particles. So this table here basically summarizes the nature of these particles. For the proton, this is a symbol that is oftentimes used for the proton. The approximate relative mass is 1, and the relative charge is +1. And of course, it's located in the nucleus. The neutron, represented by the letter N here, has about the same mass as the mass of the proton. However, unlike the proton, it has no charge, and it also resides in the nucleus. And then we have the electrons. The electrons, this is a symbol here. Now, the electrons are much lighter compared to the protons and neutrons. As you can see by this number right here, it has a negative charge. And of course, the electrons reside outside the nucleus, all right? So that's basically a summary of the nature of these particles. Then we get to another definition that you should have met before, isotopes. Isotopes are basically atoms that have the same number of protons, but the number of neutrons would be different, all right? And at this juncture, I'm going to define, again, another term that you should know about, the atomic number, oftentimes symbolized by the letter Z. That's a convention that is used, uppercase Z. And that, of course, is the number of protons in the nucleus of a given atom of a given element. And this is basically what is used to identify a particular element. Each element has its own unique atomic number, all right? So for example, sodium has an atomic number of 11. Sodium is the only element in the world, in the universe, that has that atomic number, all right? Then we have what is known as the mass number, which is symbolized by the letter A, and that is basically the sum of the numbers of protons and neutrons in an atom. And what you'll find is that different isotopes will have different mass numbers because different isotopes will have the same number of protons, but different numbers of neutrons, all right? In fact, you can determine the number of neutrons by simply finding the difference between the mass number and the atomic number. So the mass number minus the atomic number will give you the number of neutrons. And different isotopes will have different numbers of neutrons. For example, well, before I move on to the example, let me just point out this representation here, this symbolism. This is basically a shorthand way of combining information about an element's atomic number and mass number, right? So basically A would be the mass number, which is written here as a superscript. Z here would be the atomic number, which is written as a subscript. And then E would represent the symbol for the element. So for example, in the case of this isotope of chlorine, the way it is written, it tells you that 35 would be the mass number and 17 would be the atomic number. Or in the case of this isotope of chlorine, the mass number is 37 and the atomic number is 17. So basically, if you're given something like this, then you should be able to identify certain things about a particular isotope. You should be able to identify the atomic number. You should be able to identify the number of protons, which is the same as the atomic number. You should be able to identify the mass number, which is the 35. And you should also be able to determine the number of neutrons, because the number of neutrons would be, as we said before, the difference between the mass number and the atomic number, all right? So based on what we have seen here, we should be able to answer some of these questions. So here's the first question. I want you to answer it. How many protons are in chlorine 35?
Chlorine 35 has 35 minus 17.
No, number of protons, not neutrons.
Oh, protons.
Mm-hmm.
17.
Exactly. How many protons are in chlorine 37?
17.
Exactly. How many neutrons are in chlorine 37?
All right, so this one is 37 minus 17.
Exactly. So the answer would be 20, right? Exactly. So that's basically how you use these symbols to determine these, different numbers, all right? Okay, here's another example. How many protons, neutrons, and electrons are present in the 81 Br atom? So in order for us to do that, no, let me just say this. Sometimes the atomic number is not given, but you can find that out because remember, each element has its own unique atomic number, right? So all you have to do is go to the periodic table. Now, let me just say this. I don't remember if I mentioned this in the video that I posted. So let me just say this now. I have provided in Canvas tables. All right, let me show you where it's located. So if you go to Files, and then you scroll down to the folder which says Tables, right? You see 3 PDF documents here, right? Okay. The one that contains the information that we're looking for would be this one which says Tables Chemistry. I don't know what's going on with this thing. It says service. Anyway, I should be able to download it. Okay, so let me open this. Okay, this is taking its time. All right, so this is the table. Let me get this out of the way here. Excuse me. All right, let me. Okay, so this has several pages, right? The first 2 pages are different versions of the periodic table. So you have this one, and then you have the list of elements alphabetically. And then this gives you a list of ions. In fact, there are 3 pages which gives you a list of common ions, which we'll discuss later on, and so on and so forth. Conversion factors, blah, blah, blah. Some equations that you may need, not only for Chem 1, but for Chem 2. Oh, by the way, are you going to do Chem 2 this summer?
Chem 2, I might not need to take Chem 2.
Oh, okay, all right. Because I'm using basically the same information here for Chem 2. Prefixes, which I think was discussed in chapter 1, metric prefixes, like mega, kilo, etc. And then this gives you some solubility rules. We'll be using this later on. And then this is a table of electronegativity values, which we'll be using later on as well. All right, now, so I just thought I should point you to that table. So the information that we're going to need is in the periodic table, and it's for bromine, and the atomic number of bromine is 35, right? So going back to the question here, it says how many protons, neutrons, and electrons are present in this atom, right? Well, as far as the protons and electrons are concerned, that would be 35, right? Because that's the atomic number, right? And then as far as the neutrons is concerned, that would be the difference between the mass number, which is given, and the atomic number. So that would be 81 minus 35. And according
wait, no, sorry.
I'm sorry, you're saying?
No, I'm wrong.
Well, the difference would be 81 minus 35, which would be equal to 46. All right?
Okay.
And that's it. So that's basically how you answer that question. So that's a relatively simple example. All right. Now, let me talk about this term here, which is oftentimes a source of confusion for students, and that is the atomic mass, right? Students, for some reason, confuse the atomic mass with the mass number, all right? But it's very important that you understand the difference between these two. So let's talk about the atomic mass. Now, in order for us to talk about the atomic mass, you need to recognize that because atoms are very, very small, then a small unit is needed to express the mass of an atom or molecule. So, the conventional units that we use very often would be inadequate, right? So the unit that is used to express these small values is called the atomic mass unit. And by definition, one atomic mass unit is 1/12 exactly the mass of a carbon-12 atom, right? Or the carbon-12 isotope, right? So basically, that's the definition of the atomic mass unit, and it's based on that we can express the masses of small particles like atoms, protons, neutrons, electrons, and so on, all right? So it turns out that if you were to convert from the atomic mass unit to grams, then this would be the relationship between those two. One atomic mass unit would be equal to 1.66 times 10 to the minus 24 grams, all right? So that's the atomic mass unit that is used very often in chemistry and physics to express the masses of small particles. And one important point being made here, which I won't go into the explanation of because this is something that you will meet in general chemistry 2, or well, you don't have to do chem 2, you said, so you won't meet it. But this is very important. This statement right here, it says the mass of an atom is not exactly the sum of the masses of the protons plus the neutrons plus electrons, all right? And that you won't be able to understand that until we get into the chapter dealing with nuclear chemistry, which would be in general chemistry 2. So unfortunately for you, you won't get to explore that, that fact, all right? Now, this might sound a bit counterintuitive because after all, an atom is made up of these particles. So one would expect, you know, based on, I guess, common sense, one would expect that the total mass of an atom would be the sum of the masses of the protons plus neutrons plus electrons. But it turns out that that is not the case. And there's a thing called mass defect, which, as I said before, is something that you won't understand until you get to discussing nuclear chemistry, all right? So unfortunately, I won't be able to explain it here, but you need to be cognizant of this particular fact, all right? Okay, so continuing our discussion of atomic mass. Here's a question. Do all isotopes of an element have the same mass? And your answer is what?
No, because it has different amounts of neutrons.
Exactly, right. So that's the reason why the atomic mass would be different for different isotopes of an element. So in order to get a number which represents the average mass of a particular atom of an element, which takes into account the existence of the different isotopes, we have what is known as the weighted average, right? Masses of the naturally occurring isotopes of that element. And that is expressed as the atomic mass for the particular element. Now, as an example of how this is calculated or how this is determined, we're going to use this example right here. So here we have two isotopes of carbon. Actually, there's more than two, but these are the two one that exist in most abundance. You have carbon 12, where its percent abundance is 98.892%, and you have carbon 13, whose percent abundance is 1.108%, all right? Now, let me just say something here. When it comes to naturally occurring isotopes for different elements, what you'll find throughout the universe is that these percentages exist, or these isotopes, I should say, exist pretty much as fixed percentages, right? So for example, if I take up a sample of a substance which contains carbon, and if you could separate the isotopes, what you'll find is that 98.892% of the carbon atoms present would be carbon 12, and 1.108% of the rest would be carbon 13, all right? And that is true not only for carbon, but true for all other elements that exist in nature, right? Basically, the percentage abundance of each isotope for the respective elements is pretty much fixed. I mean, there's some differences throughout the universe, but you know, approximately speaking, it would be the same. So this question, this example is asking for you to use the data above here to determine the weighted average atomic mass of carbon. And it gives you some data concerning the masses of the carbon 12 atom and the carbon 13 atom, all right? So let me create some space here. Let me bring this up a bit. Okay, because I need to write down here. Okay, so get my pen, get my black ink. Okay, so the way we would actually carry out this calculation is that we would take the mass for carbon 12. Let's deal with carbon 12 first. For carbon 12, we would take the mass of carbon 12, which is given here, and we have to deal with all the digits here. So this would be 12.0000, how many zeros? 5 zeros. AMU multiplied by the fractional abundance, which is 0.98892. 0.98. I hate when this happens, and I don't know how to stop it. Go back here. Okay, 0.98892. All right, and then we have a similar setup for carbon 13, which the mass is 13, which is given here, by the way, 13.00335 AMU times, and the percent abundance or the fractional abundance here is 0.0118. Okay, let me get rid of this, get rid of this, and correct. Okay, so there should be a 0 here, and there should be 0.0118. Okay, so we have to work out these, right? So let me start off with, let me work out the carbon 12 ones. So that would be 12 times 0.98892. And according to my calculations, when rounded off to how many sig figs? 5 sig figs. So this is going to be 11.867 AMU. All right. And then in the case of carbon 13, 13.00335 times 0.01108. So I need to correct this here. Let me correct this here just to make sure everything is accurate.
Yeah, I was going to say, Professor, yeah, 108.
Yeah, that's an oversight on my part. Let me correct that. So this would be 0.8. All right. So according to my calculations, the answer I got for that part is 0. How many sig figs? 1, 2, 3, 4 sig figs. So this would be 0.1441 AMU. Daggone it. AMU. Okay, let me erase this here. I'm going to figure out how to deal with this crap. Okay. And then we add these two numbers here. So let me do that calculation on my calculator. So that's 11.867 plus 0.1441. And according to my calculations, that would be equal to 12.011 AMU. And this would be the final answer, which represents the weighted average atomic mass of carbon, taking into account the percentages and the masses of the different carbon isotope. And this particular number here, right, if you look in any legitimate, this number here, if you look at any legitimate periodic table, what you'll find is that that number will be present for the carbon in the box for carbon in the periodic table. So if you go to the periodic table, let me go to the periodic table in the, where is it? Let me go here. Right. So if you go to the periodic table here and you look up carbon, there are two numbers that you're going to see for carbon. One would be the atomic number, which is 6 for carbon, and the other one would be the atomic mass, which is 12.01. And that atomic mass is actually the weighted average atomic mass for carbon, taking into account the mass of the different carbon isotopes and the percent abundance of the different carbon isotopes, all right? And that's how all these numbers are obtained for the different elements. For oxygen, that's 16.00. For fluorine, it's 19.00. For iodine, it's 126.91, and so on and so forth. So all these numbers that you see here for the atomic mass, that represents the weighted average atomic mass of these elements, taking into account the respective masses of the isotopes and the percent abundances of the isotopes, all right? Okay, so what I'm gonna do here is take a break. I probably should have told you this, but what I plan to do for this course is that I will basically talk for about 50 minutes and then take a 10-minute break. So I've gone more than 50 minutes right now. So it's now 10:30, and we're going to restart at 10:40. All right?
Sounds good.
Okay, so hopefully, let me see. Let me see. Okay, so your fellow student, he has not joined yet. I'm going to send him an email just to let him know that the class is going on right now. All right, so I'm sorry. I'm sorry.
Is there only two of us in the classroom?
Yes, and that's the reason why I I didn't, I wasn't sure the class was going to run. So it's basically being run as an independent study.
Okay.
Yeah.
I
So
do have a question about the lab.
oh yes, I know you'd have questions about the lab.
Yeah, that's gonna be in person. Yeah.
That definitely will be in person, right? And
Okay.
I have to apologize for that because I didn't realize until this morning, in fact, just before class started today, that I did not publish the canvas for that lab. I put up everything in there, including announcements, and then I realized that this morning that it wasn't published. I forgot to press the button for publishing.
Okay.
So I'm going to deal with that during the lab period. All right.
All right.
Okay. So let me do a quick send email to your fellow student.
All right. And so yeah, it's break time then. Yeah.
Yeah, you can, stretch your legs, whatever.
Okay.
We're going to restart at 10:40.
All right. Thank you.
Yeah, no problem. Okay, I am back and I see Mr. King. Can you hear me?
I can hear you.
Okay, good. All right. So just to let you know what has happened in your absence, we have started chapter 2. So we're basically in the middle of chapter 2. We just did this example. Oh, by the way, I don't know if I don't think I said this to Mr. Perez earlier. All the PowerPoints that I'm teaching from. Okay. Hold on 1 minute. Hold on a minute. So yeah, sorry about that. All the PowerPoints I'm teaching from, they're located in Canvas. Let me just show you where you can find it. So, so this is located again under the files link. And then if you go to where it says lecture, the folder labeled lecture, that's where you're going to see all the PowerPoints that I'll be teaching from. So you can follow along with that. You can review from that. And again, if you have any questions, feel free to ask if there's something that you don't understand from the PowerPoint or from the lecture. And as I told Mr. Perez earlier, I'm also recording. In fact, we're broadcasting live now on YouTube, and it will be recorded. So if you want to review that as well, that's fine. You can go ahead and I'll provide that YouTube link in the module section as well. All right. Okay, so let's continue the discussion here. So we just talked about atomic mass. So the next thing we're going to talk about is the periodic table. And the first person that is credited with coming up with a version of the periodic table is a Russian scientist by the name of Mendeleev. And Mendeleev discovered that if you arrange all the elements, well, at the time, during his time, because the number of elements that has been discovered since his time has increased since then. So basically what he did was that he arranged all the known elements according to their atomic masses. And it's very important that you understand that that's basically what was used to identify elements in those days, because back then nobody knew anything about protons, and therefore as a result there was no such thing as the atomic number for an element. So basically all he had to work with in terms of identifying elements would be their atomic masses. All right. So what he did was that he arranged the elements that were known back then according to the atomic masses. And what he found was that as you go from one element to the next, and then after you get to so many elements, then the properties tend to resemble each other. In other words, they tend to repeat after so many elements. So what he did was that he arranged elements with similar properties in columns, and these are now called groups. But of course, after arranging the elements across in rows, which are now known as periods, all right? So he arranged some elements according to their according to their atomic masses in a row. And then when you get to an element that has a similar property to the first element in that row, then he basically restarts another row with the elements matching up in terms of the properties that they display in groups. And based on his periodic table, he discovered that there were certain gaps that appeared in his periodic table, in his version of the periodic table. And what those gaps basically represent are elements that were not yet discovered. So, however, based on the positions of those gaps, he was able to predict with a high degree of accuracy the properties that these undiscovered elements will display, right? And I say with a high degree of accuracy because when these elements were discovered and when these properties were compared to the one that he predicted, there was a very close correlation. And this is the original periodic table that he came up with. Of course, this is translated into English. And there are some question marks here, which represents elements that were not yet discovered, such as the question mark here question mark here, and so on and so forth. So just to give you an example of an element that was not discovered during Mendeleev's time, and then it was discovered after that, and what he predicted in terms of the properties and what was actually discovered. He predicted that a particular element known as, well, he called it ecosilicon. We now call it germanium. So in 1871, he predicted that the atomic mass of this element would be 72. When germanium was discovered, it was determined that the atomic mass is 72.6. So as you can see, there's a close correlation as far as what is predicted and what was actually observed. The density, he predicted that the density of germanium or ecosilicon is 5.5. It was determined that the density of germanium is 5.47. All right. He predicted that the color of germanium would be dirty gray, right? And it was discovered that the property of germanium is grayish white. Now, I don't know the difference between dirty gray and grayish white. As far as I'm concerned, both are the same. All right. He predicted that the density of the oxide of germanium would be 4.7. It was determined to be 4.703 grams per cm cube. He predicted that the boiling point of the tetrachloride of germanium would be below 100 degrees. So he could not, accurately predict, in the case of temperature, what its boiling point would be. And it was determined that when germanium was discovered, it was determined that its chloride boiling point would be 86 degrees Celsius. And then finally, he predicted that the density of the same chloride would be 1.9 grams per centimeters cube. And it was discovered that the actual density is 1.887 grams per cm cube. All right. So as you can see, he observed some properties which basically closely correlate to the actual properties that were discovered when germanium was discovered. All right. Of course, back then he did not know the reason why. And the reason why this happened was discovered about more than a century after he came up with his version of the periodic table. Okay, so this is basically the modern periodic table. Of course, with the discovery of other elements, there were modifications and changes to the original periodic table that he came up with. And this is what we end up with as the modern periodic table. And as you can see, in the periodic table, we have columns which are numbered with a number and letter. There are actually two systems of numbering the columns. There's one system, which is an older system, one that I'm accustomed to from my high school days, where each column has assigned to it a number followed by a letter. So this is group 1A here, then 2A, then you have 3B, 4B. These are basically called the transition elements. We'll talk about these later. And then over here, we have 3A, 4A, 5A, all the way over to 8A. And then we have the inner transition elements right here, which actually should be placed right in this slot right here, all right? And there are several ways of categorizing the different elements in the periodic table. So one broad categorization would be metals, nonmetals, and noble gases. Metals, nonmetals, and metalloids. That's what I should have said, right? And the metals are in the orange colored boxes right here. The nonmetals would be in the purple boxes right here. However, as far as the metalloids are concerned, there are 8 of them, which lies exactly on one side or the other of this zigzagged line that you see here. So if you look carefully at most periodic tables, you'll see this line right here. This line basically represents the line of demarcation between metals and nonmetals. All right. So the metals would be to the left of that line. The nonmetals would be to the right of that line. And as you can see, based on that categorization, the vast majority of elements in the periodic table will be metals. All right. And the metalloids, as I said before, would lie directly on one side or the other of that zigzagged lines. So we're talking about elements such as silicon, germanium, arsenic, antimony, tellurium, and astatine. So these are basically the metalloids, right? Which is a minority group in terms of the total number of elements that you can identify in the periodic table. Okay, let's move on from the periodic table and talk about molecules and formulas. And again, this is something that you should have met before in your introductory chemistry class. And let's start off with a discussion of the molecules. So molecules are basically substances, or I should say a collection of atoms that are held together by covalent bonds, right? So basically it's a group of two or more atoms that are held together by covalent bonds. And we can summarize the makeup of a molecule in the form of a molecular formula, which gives you the number of every type or each type of atom present in a molecule. Now that is different from what we call the empirical formula, which gives you the ratio of atoms of elements in a compound, all right? So just to give you an example of the difference between a molecular formula and empirical formula, for hydrogen peroxide, the molecular formula is H2O2. For the empirical formula, it is simply HO, right? So in the case of the molecular formula of hydrogen peroxide, what this tells you is that for every molecule of hydrogen peroxide, you have 2 atoms of hydrogen and 2 atoms of oxygen, all right? So therefore, that's a molecular formula. The empirical formula gives you the ratio of hydrogen to oxygen that is present in the compound, which of course would be 1 to 1, all right? So in the case of this other example, octane, the molecular formula is C8H18. So what would you say the empirical formula is? Can anybody tell me what the empirical formula of C8H18 is?
Would it be C4H9?
Exactly, C4H9. Of course, all you have to do is divide the subscripts here by, what's the term they use in math? The highest common factor, if I'm not mistaken, which would be 2 in this case. So 8 divided by 2 will be 4, 80 divided by 2 will be 9. So the empirical formula will be C4, I'll write it right here, C4H9. All right. Okay. So another way of representing molecules is using what are known as structural formulas. And structural formulas basically shows you how the atoms are connected to each other in a molecule. So the example that is shown here is the example of acetic acid, right? So we have what is known as a ball and stick model. I don't know if any of you have to do organic chemistry, but in organic chemistry, you're going to find that representation is very important because when it comes to reactions that organic compounds will undergo, in a lot of cases, these reactions are dependent on the shapes of molecules, and therefore it is very important when it comes to these reactions that you have a good feel for the 3-dimensional arrangements of the atoms, all right? So this represents the ball and stick model for acetic acid, and the convention that is normally used when it comes to this representation is that the black spheres represents carbon, and the white spheres represents hydrogen, and then you have different color spheres for other atoms, right? So as you can see here, this carbon atom is bonded to 3 hydrogen atoms, and at the same time, it's bonded to this carbon atom, which is bonded to 2 oxygen atoms. This carbon is bonded to this oxygen atom by a double bond. This carbon is bonded to this oxygen atom by a single bond, and then this oxygen is bonded to a hydrogen atom here, all right? So that's basically showing you how the atoms are connected, and also giving you a picture of the 3-dimensional shape of the molecule. Now, this representation here, we call it a space-filling model, right? And this type of representation is oftentimes used in high-level research because when it comes to certain systems, you have to take into account not only how the atoms are connected to each other, but also the amount of space that is taken up by the different atoms. And that can have a profound effect on certain properties that these substances will display, especially when you get into, for example, medicinal or pharmaceutical chemical research, right? Basically, in these types of research, we are looking at how certain molecules interact with biological systems. And in order for us to do that, we have to look at the shapes of molecules and how they can fit into, for example, what we call an active site in order to trigger certain physiological changes in biological systems. So that's basically the space filling model for acetic acid. All right, let me see here. Okay, so let me move on now to nomenclature. So when it comes to, well, let's talk about what we mean by nomenclature. Nomenclature is basically dealing with the system of naming compounds. And there is an organization known as IUPAC. Let me write it down here. Okay, why is this thing not? Okay, something is wrong here. Let me. Hold on. Oh gosh. Okay, now it's working. All right. So there's an organization known as IUPAC, IUPAC. And IUPAC stands for International Union of Pure and Applied Chemists, right? And as suggested in the acronym, it's an international organization, and there's one division in that organization whose sole purpose is to come up with rules for naming compounds, right? And they meet regularly. I don't remember exactly how often. I think it's twice, or I think it's every 2 years, if I'm not mistaken, right? But basically, these are the guys who come up with the rules for naming organic compounds and chemical compounds, generally speaking, all right? And that's important because what you'll find is that because you have new compounds being made literally every day, then sometimes you'll find that the new compounds cannot be named on the current system of naming compounds based on what IUPAC has come up with. And therefore, IUPAC would have to meet, or the committee would have to meet in order to make new rules or change old ones in order to fit the new compounds, all right? So what we're going to discuss are the rules for determining the names of some simple compounds. So let me erase this here. And let me go back to this. Okay, so as stated here, the rules are very important because, as stated here, we could have a specific name for each compound, but of course, with millions of compounds that exist, it would be a bit of a challenge to memorize each name, right? So, and the same is true for organic compounds. Organic compounds is even greater in numbers, and therefore, if we come up with a unique name for each of them, then of course, the challenge would be to memorize these names, which would be a bit of a challenge, all right? So therefore, there's a systematic method that has been developed by IUPAC with rules and conventions for naming compounds and also determining the formulas. So basically, if you know the formulas of the compounds based on these rules, you can determine the name and vice versa. So what we're going to look at is how do we name what we call binary molecular compounds, right? So when we're talking about binary molecular compounds, we're talking about compounds which contain only 2 elements. And let me just give you some examples of binary molecular compounds. So I'm talking about examples such as H2O, CO2, SF6, ICl2. These are all examples of binary molecular compounds because in each case, they're made up of 2 elements. Now, the number of atoms of each element may vary, right? But the point is that there are only 2 elements that are present per molecule of each compound, all right? So we're talking specifically about molecular compounds, compounds that exist as molecules. So how do we name these compounds? Well, the compound name will consist of 2 words. The first word would be the name of the element that appears first in the formula, all right? The second word would be the stem of the name of the second element, but it will end with the suffix IDE, all right? So that's basically what it comes down to when it comes to naming binary molecular compounds. Now, there is another thing that you have to take into account when naming binary molecular compounds, and that is that we have to modify the names using the appropriate prefixes to indicate the number of atoms of each element that is present in the molecules. And I'm going to say more about that because there are some exceptions when it comes to including prefixes, which we'll talk about. Now, before we get to that, we have to ask ourselves the question, how do we determine which element is named first? Now, what you could do, which I don't think you'd want to do, is memorize this table here, which gives you the order of the different elements as to which one is named first. A better way of determining that is that we obey this rule of thumb. And the rule of thumb is that the element that is furthest down in the periodic table and to the left in the periodic table is usually written first. In other words, the least or the less electronegative element, right? Now, that brings me to going back to the table that I've posted in Canvas, because one page of that table, let me see if I can find it. Let me go here. Where is that table? I think this is, nope. Okay, here it is. All right, so the very last page on this table gives you the electronegativity values of the different elements, right? So basically you could use this to help you to determine which element is indicated first. So according to IUPAC, the element which has the lowest, the least, I should say the less electronegative value is the one that is indicated in the formula or in the name first, right? So for example, if you have a compound which is consisting of two elements, arsenic and sulfur, the question is asking which element is named first. Well, if you go to the table and you look at where arsenic is, which is here, and sulfur, which is here, arsenic has a lower electronegativity value compared to sulfur. So therefore, arsenic would be indicated first in the name or the formula, and then the sulfur would be indicated next, all right? So that's basically how you determine which element is indicated first in the name and or in the formula. Okay, so here are some examples of binary molecular compounds and how they're named, and the type of prefixes that you use, all right? So these are the prefixes that you're going to use to indicate the number of atoms in each molecule. So it's very easy. Mono is for 1, di is for 2, tri is for 3, and so on, all the way to deca for 10. And there are more, but for our purposes, we'll just stop at 10, all right? Now, the first example I want to point out here is this example, NO. That's the formula for this molecule. The name of this compound is nitrogen monoxide. Now, let me just mention something here, because this is a bit of an exception to the rules concerning prefixes. Let me go to my writing function here. Okay, so remember, to indicate that there's one atom of an element, we use the prefix mono. So you might be wondering, why is this not called mono nitrogen monoxide? All right, because after all, there's one atom of nitrogen here and one atom of oxygen here. Well, the reason why is because according to IUPAC, if the first atom in the formula has only one atom represented, then you do not use any prefixes. In other words, the mono prefix is not used to indicate that you have only one nitrogen atom, because the nitrogen is indicated first in the formula, right? So that is a bit of an exception to the rule using prefixes. So basically, if the first atom, or the first element, I should say, has one atom in the formula, then no prefixes are used. All right, so that's a bit of an exception to the use of prefixes, all right? So the same is true for nitrogen dioxide. Again, there's one atom of nitrogen, which is the first element indicated in the formula. So therefore, we do not use mono in front of the nitrogen, the name of this compound would be nitrogen dioxide. And of course, dioxide because you have 2 atoms of oxygen here, all right? In the case of the third example, N2O3, you have 2 nitrogen atoms and 3 oxygen atoms. So the name of this compound is dinitrogen trioxide, all right? In the case of the fourth example, where you have 2 nitrogen atoms and 4 oxygen atoms, the name of this molecule is dinitrogen tetroxide. In the case of the fifth example, you have 2 nitrogen atoms and 5 oxygen atoms. The name of this compound is dinitrogen pentoxide. All right. And then in this example here, again, there's only 1 atom represented for the first element, which is sulfur. So there's no monosulfur here. So the name of this compound is sulfur hexafluoride. In this case here, you have 1 atom of iodine, 7 atoms of fluorine. So the name of this compound is iodine heptafluoride. In this case here, you have 4 phosphorus atoms, 8 oxygen atoms. So the name of this compound is tetraphosphorus octoxide. All right, and so on and so forth. So basically, that's how we name binary molecular compounds. All right. Okay. How much time do we have left in this section? Let me see here. Okay. All right. So any questions about naming of binary molecular compounds? Any questions? Any questions?
I have no questions now.
Okay. All right.
No questions.
All right. So let's see if you can answer these questions. So this question says, write the molecular formula and the name of a compound for which each molecule contains 6 oxygen atoms and 4 phosphorus atoms. All right. So what would be the formula? Let's write down the formula first. So what would be the formula? Now, remember, before you answer the question, there's one thing I need to remind you. Remember, you have to figure out which element is indicated first, right? You have 6 oxygen atoms and 4 phosphorus atoms, all right? So first thing you have to ask yourself is which element would appear first? Would it be the oxygen or the phosphorus?
The phosphorus first.
Exactly. The phosphorus will go first, and then the oxygen. And then now you have to figure out what the subscripts are. Well, it says 6 oxygen atoms, right? And 4 phosphorus atoms, right? So that's the formula. So now we have to figure out the name. So what would you say the name of this compound is? What's a prefix for 4? Let's deal with that first, for the phosphorus. What's a prefix which represents 4?
Tetra?
Tetra, exactly. So let's write that down. Tetra, okay? I hate when this happens, man. Let me erase this here. Okay, so tetra. Tetra, and then what? What comes after the tetra?
Phosphorus?
Phosphorus, okay. And then what? What's a prefix for 6?
Is it hexaoxide?
Hexa, okay, so the prefix would be hexo, or hexa, I should say. So the name of the compound would be tetraphosphorus hexaoxide, or, and I think IUPAC allows this. Let me correct this again. Okay. Yeah, so IUPAC actually allows you to actually express this as hexoxide. All right. So instead of including the A in the name, instead of saying hexaoxide, you can simply say hexoxide as well. That is also allowed by IUPAC. All right. And that's it. Okay. So that's the name of this compound, tetraphosphorus hexoxide, or simply hexoxide. Okay, so that's the first example. The next example says, write the molecular formula of phosphorus pentachloride. Okay, so let's deal with that. What would be the molecular formula for phosphorus pentachloride?
Would that be wait.
No, this one, phosphorus pentachloride.
Oh,
the question is asking for the formula.
Okay.
Mm-hmm.
So that's P,
Mm-hmm.
and then penta is 5, so chloride 5.
Cl, and then 5. All right. And then the next question is the name of S2F10. So they gave you the formula, S2F10, and they're asking for the name. So what would you say the name of this compound is?
Is that disulfur?
Disulfur.
Disulfur.
Decafluoride?
Decafluoride, exactly. All right, so that's basically how you name this compound. All right. Okay, any questions about any of these examples? Any questions?
No, no questions.
Okay, all right. So we talked about binary molecular compounds. So what we're going to talk about now are ionic compounds. And we're going to talk about ions in more detail. But for now, what you need to remember is that an ion is basically an atom. And this is in regards to monatomic ions. We're going to learn about polyatomic ions later on. But for now, let's deal with monatomic ions. So a monatomic ion is one where you have an atom that either gains or loses an electron. All right. Now, key thing you need to remember is that there's no change in the nuclear composition of the atom when it converts to an ion, right? The only thing that will change is the number of electrons, right? Depending on whether or not the electrons are being lost or gained. Now, if you have electrons being lost from an atom, then the resulting ion will have a positive charge and it's called a cation, all right? On the other hand, if an atom gains electrons, then it will end up with a net negative charge, and this ion is called an anion, all right? So those are the types of ions that we'll be dealing with. Now, when you have an ionic compound being formed, basically it's as a result of a combination of the anions and the cations coming together. And what you'll find is that you won't have any discrete units of a particular ionic compound as you would have in the case of a molecular compound. So for example, in the case of water, which is a molecular compound, you can actually identify discrete units, which would be a combination of one oxygen atom to two hydrogen atoms. In the case of ionic compounds, you don't have that formation of discrete units. Instead, what you have is something looking like what you're seeing here on your screen, where you have the ions assembling themselves in a particular orderly fashion, and you have simply an array of ions in an ordered way, all right? So basically, in this particular representation here, you have the green spheres representing the chloride ions, and the purple spheres here representing the sodium ions, and this is how they're assembled, all right? So that's basically what you'll find in ionic compounds. You don't have any discrete units of ions. There's no such thing as a molecule when it comes to ionic compounds, all right? In any case, what will happen is that the total number of positive ions, which would be the cations, would be equal to the total number of negative ions in the case of sodium chloride, so that the entire compound would be electrically neutral. In other words, the charges will cancel out each other, all right? So, as I said before, monatomic ions are formed as a result of atoms gaining or losing electrons. And the type of ions that are formed is influenced in part by the positions of the elements, the respective elements in the periodic table. So as stated here, group 1A metals will form ions which will carry a +1 charge. Group 2A metals will form ions that will carry a +2 charge. And then when it comes to group 3A metals, they tend to form ions with a +3 charge, including aluminum. And then when it comes to non-metallic ions that belongs to these groups, 5, 6, and 7 respectively, the ions that are formed will tend to have charges of -3, -2, and -1 respectively, all right? And then we have the elements that are known as the transition metals, otherwise known as a group B metals, right? Now, when these elements form ions, in a lot of cases, they can form different ions of different charges, right? And in order to indicate these charges in the names of these compounds that contain these ions, we include a Roman numeral represented or right beside the formula for these ions to indicate the actual charges carried by these particular ions, all right? So that is true in the case of a lot of transition metal ions. However, there are a few transition metal ions that have only one charge, and therefore Roman numeral is not used when indicating the charge on these ions. And we're talking about ions such as silver, zinc, and cadmium. And in fact, there is, again, in Canvas, let me go back to the table, 3 pages which contains the list of common ions. So let me show you what we're talking about here. Okay, so this is the first page here, which is turned sideways. Let me turn it right side up. Okay, so if you look at this table here, you see, the different ions and their charges. And down here in the transition metal region, the B groups, elements, you see that there are certain elements that can display more than one charge. So just to highlight a couple of examples, titanium can exist as titanium 4+ or titanium 3+. And if you look closely at the names, let me expand this, blow this up a bit. If you look closely at the names indicated here, the name of the ion which contains a +4 charge is called titanium 4, in parentheses and Roman numerals, right? So that's titanium 4, whereas in the case of titanium 3+, you have the name titanium, and then you have the Roman numeral 3 in parentheses. So the 4 and the 3 here indicates the charges that are carried by the titanium, the respective titanium ions, all right? And you see similar examples for vanadium, for chromium, for manganese, and others, all right? For palladium, for nobelium, and gold, and platinum, and so on and so forth, mercury, etc. All right? So that will become important when it comes to naming compounds containing ions as opposed to molecular compounds. Okay, so let me go back to the PowerPoint here. And okay, so based on what we have learned, we should be able to answer these questions. So let me help you out with the first one here. The question says you're to determine the formula for calcium chloride. So what you would have to do first is to identify the charges carried by the respective ions, right? So since you'll have access to the tables, what you do is look up the formula for the calcium ion. And the formula for the calcium ion is Ca with a +2 charge, all right? Let me do this again. All right, so that's Ca with a +2 charge. And then if you look up the formula for the chloride ion, it's going to be Cl minus, all right? Now, remember we said that in any ionic compound, the total number of plus charges must be equal to the total number of negative charges. As we have it right now, the calcium has a +2 charge and the calcium has a -1 charge. So the charges are not balanced based on what we have here. So what we need to do is, in this case, multiply the number of chloride ions by 2 so that this 2 would multiply the negative charge here. So that would be -2 total for the 2 chloride ions, which will counterbalance the 2 plus charges here for the calcium ion. So when we put this together, the final answer becomes CaCl2. So this 2 here that we use to multiply the chloride ion by, we put that down here as a subscript. So therefore, this would be the final answer for the question of what's the formula for calcium chloride. Okay, so if you understand that, then you should be able to figure out the formula for magnesium oxide. So how would you determine the formula for magnesium oxide?
Magnesium has a +2 charge.
Okay, so Mg 2 plus, okay. And what about the oxide ion?
And then oxide has a, does it have a negative charge?
Negative what?
I guess it'd have to have a -2 charge.
Exactly, -2, all right? Okay, so what would be the resulting formula for magnesium oxide?
Mg2 oxygen 2.
Well, you're partially right. And your answer kind of gives me the opportunity to explain something here. Let me go back to this. Okay, so the actual formula would be MgO, all right? So there's no reason, there's no, how should I put this? There's no reason to multiply this by 2 or multiply this by 2. And the reason why is because this -2 charge here cancels out the +2 charge, right? So therefore, basically, the answer would simply be MgO. Let me erase this here. Right? So that would be the final answer. Go back.
I see.
Right, so this would be the final answer right here, all right? Okay, so that brings us now to the next example. What are the names of MgS and CrCl3, all right? Okay, so let's deal with A. So this is kind of the reverse of what we were just doing in the first example. You're given the formulas and you're asked for the names. So what would be the name of MgS?
Would it be magnesium sulfide?
Exactly, magnesium sulfide. All right, very good. All right, so what about B? Now, you have to be careful in the case of B, right? So what say you would be the name of CrCl3? I'm sorry, CrCl3.
Is that going to be chromium trichloride?
No. Okay, so that gives me the opportunity to talk about something which I didn't mention before. When it comes to ionic compounds, we do not use the prefixes that we would have used in the case of molecular compounds, right? So we do not use prefixes like tri to indicate that there are 3 chloride ions. Okay? So that's one reason why what you said is not correct, all right? No prefixes are used when it comes to ionic compounds. We only use prefixes when it comes to molecular compounds, all right? Okay, now you're right about the fact that you're starting off with chromium, but that's not it, or that's not just it. There's something else you need to do. So what do you think you need to do?
That's when you put the Roman numeral 3 in front
Exactly,
of it, right?
right. You need a Roman numeral because chromium is one of those transition elements that can display more than one charge, right? If you go back to, let me show you here. If you go to the table that I showed you here, you see that chromium can exist as +3, but it can also exist as +2. So the question you have to ask yourself is, which one would it be in this compound? And the answer lies in the fact that each chloride ion, excuse me, will have a -3 charge. Hold on 1 minute, sorry, let me clear my throat. Each chloride ion will carry a -3 charge, all right? And if there are 3 of them, that means that the total number of charges for the 3 chloride ions will be -3, which would mean that the total charge carried by the chromium would be +3. So therefore, you need to indicate the charge on the chromium by using, well, by writing in parentheses the Roman numeral 3. All right, and then chloride. And that's basically how that is done. All right. Okay, any questions about this? Any questions? Any questions?
No questions.
No questions? Okay.
I do have a question.
Yes, sir.
So for, so all right, so for ionic compounds or
Mhm.
ionic bonds, you have to know that it's metal and non-metal, right?
Exactly, right. Well, in most cases, when it comes to monatomic ions, yes. Ionic compounds are typically formed between metals and non-metals. Now, there are some exceptions to that. For example, when you're going to see in the case of polyatomic ions, where you can have, for example, ammonium chloride, where there are no metal ions existing, right? We'll get to that later on. But when we're dealing with monatomic ions, right? Ionic compounds is formed between a metal and a non-metal, like magnesium and sulfur, chromium and chlorine, and so on and so forth. All right?
Okay, I got you.
All right. Okay, now, in terms of the symbols of monatomic ions, we have some examples right here. And there are certain patterns that emerges, which we talked about earlier. Elements in groups 1A tend to form ions with a +1 charge. Elements in group 2A will form ions with a +2 charge. Elements in group 3A would form ions with a +3 charge. And to a lesser extent, elements in group 4A will form ions with a +2 charge. There are some exceptions to that. For example, carbon will not form +4 or +2, I should say, because it's a nonmetal. And the element below carbon is silicon, and the element below silicon is germanium. So those typically do not form ions, all right? And then we have the non-metallic elements in groups 5A, 6A, and 7A. And you'll see that the elements in group 5A, they tend to form ions with a -3 charge. Elements in group 6A, they tend to form ions with a -2 charge. And elements in group 7A will tend to form ions with a -1 charge. And as I mentioned before, down here we have the transition elements. And in some cases, in fact, in most cases, they will form ions with more than 1 charge. But there are other cases like nickel, zinc, silver, and cadmium. They form only 1 charge or only ions with 1 charge. Scandium also is an example of that. But for the most part, most of the ions, actually nickel, if I'm not mistaken, forms, let me check something here. Let me go back to the table here. I think nickel forms, yes, nickel forms +2 and +3. All right, so you know, if you're trying to figure out which ions we're dealing with in terms of the ones that can form more than 1 charge, please consult this table, right? And not only this page, but the next page here, which gives you another list, and the next page after that, which gives you another list, right? I've decided to include these 3 pages because there are some ions missing in one page, which would be available in another page and so on. So that's why I provide those 3 pages. And you can refer to these tables when it comes to figuring out the charge carried by different ions, all right? Okay, going back to the PowerPoint here. So this is just highlighting some examples of different transition elements which can display ions of different charges, like titanium. Titanium can exist as the +2 ion and +4. Copper can exist as copper-1 and copper-2, all right? And this is just asking what is the charge on the zirconium ion, zirconium-4 ion, which is, of course, +4. Okay, so how do we name these compounds based on what we have just discovered? How do we name binary ionic compounds? Binary ionic compounds are made up of monatomic cations and anions, all right? So these combinations must be electrically neutral. In other words, the total number of plus charges must be equal to the total number of negative charges. And then there's a term here which we call the formula unit, which is basically the simplest collection of cations and anions that represents an electrically neutral unit. So for example, an example of a formula unit would be, let's say, let me squeeze it in right here, NaCl, that's a formula unit, or calcium fluoride, that's a formula unit. We use formula units instead of molecules when it comes to ionic compounds, all right? The formula unit basically represents the empirical formula for the ionic compound, all right? So another example of a formula unit would be let's say, lead to chloride, all right? So these are all examples of formula units. Okay, so to write down the formula for an ionic compound, we have to combine the proper number of each ions present to form a neutral compound. So basically, you have to make sure that the total number of plus charges are equal to the total number of negative charges. And then to name the binary ionic compound, the convention is that you name the cation first, the positively charged ion first, and you follow that up with the name of the anion, all right? So, and one other thing I need to mention is that the monatomic anion names always end with IDE, all right? Okay, so, hold on, I thought there was an example coming up. Okay, I think I spoke too soon. Okay, so before we move on to the example, let me see how much time I have left in this section here. Okay, you know what? Let us take a break, and then we'll move on to a discussion of polyatomic ions, all right? So as I was saying to Mr. Perez before, the way I'm going to conduct this class is that I'll be teaching for 50 minutes and taking a 10-minute break between the 50-minute intervals, right? So let us take a 10-minute break now, and you can, you know, stretch your legs, do whatever you need to do, and then we'll get back here and restart, all right?
Okay.
Okay, sounds good.
Mm-hmm. Okay, folks, I'm back. All right, so let me, hold on 1 minute. Okay, so let's proceed to a discussion of polyatomic ions. By the way, can you all hear me?
Yes.
Okay, good. All right. So let's talk about polyatomic ions, which is different from monatomic ions in that in the case of polyatomic ions, you have basically a group of atoms that are covalently bonded, and that group of atoms as a unit is carrying a charge, all right? So that's what a polyatomic ions is. And what you'll find is that when it comes to polyatomic ions, you have much more of them being negatively charged than those that are positively charged. All right. Now you can ignore this line right here. I'm not a big fan of memorizing the formulas of polyatomic ions because you'll have access to the tables. You can refer to those tables when it comes to determining the formulas. And what you'll notice is that in some cases, you will have some prefixes in the names of these polyatomic ions, such as hypo and per, which basically indicates to some degree the number of oxygen atoms that are present in these polyatomic ions. And these polyatomic ions, by the way, that contain oxygens, they're also known as oxoions, or oxoanions, I should say. Also, what you'll find is that in some of the names of these polyatomic ions, they will have an ITE ending, ite, or ATE ending, ate, which again, to some degree, expresses the amount of oxygen that is present in these polyatomic ions, all right? And this table here is a list of polyatomic ions along with some compounds which contain these ions, all right? Of course, the more comprehensive list is given in the tables that I provided for you. So, just to highlight a couple of examples, the carbonate ion has this formula, CO3 with a -2 charge. The cyanide ion is basically Cn with a -1 charge. The oxalate ion is C2O4 with a -2 charge, and so on and so forth. All right. Okay, so we're going to see now how we name compounds which contain these types of ions, right? So this question is asking for you to write the formula for, and it gives you the name, sodium sulfite. So again, what you would do, as we saw in a previous example, is that you go to the table and you look up the formula for the sodium ion, and that would be Na+. And you do the same thing, and you look up the formula for the sulfite ion, and that would be SO3 2-. So here we have a situation where we have a +1 charge here for the sodium, and here we have a -2 charge. So how do we get the charges canceled out? We put a 2 here in front of the sodium, and when we combine these together, you're going to get Na2SO3. And that would be the formula for sodium sulfite, all right? Okay, now in the case of B, this is a bit different because in this case, we're dealing with naming, or I should say writing down the formula for ammonium sulfate. So if you consult the tables, you see that the formula for the ammonium ion is NH4+, and the formula for the sulfate ion is SO4 2-. Now, again, we have an imbalance of the charges. We have a +1 charge here. We have a -2 charge here. So how do we balance the charges? Well, just like we did here in the case of sodium sulfite, here we're going to multiply the ammonium ion by 2. So the charges are now balanced. But things are a bit different here in terms of writing down the final answer. And that is, in the case of the ammonium ion, in the final answer, what you'd have to do is put the formula for the ammonium ion in parentheses, and then put the 2 outside as a subscript. And then we follow that up with the sulfate ion, SO4, and that's it. So the formula for this compound is this right here. All right. And the reason why we put a parentheses around the NH4 is because the ammonium ion is a polyatomic ion. And that's how you deal with polyatomic ions when you're writing down their formulas. If there's more than one of them in the formula, right, we have to put the formula for the polyatomic ion within parentheses and then indicate the number of atoms or the number of those ions outside the parentheses as a subscript. All right. So that's basically how we deal with that. All right. So the next examples, now they're asking for you to give the name based on the formulas that are given. So let's see if you can do this one. NaCN. What do you think the name of that compound is? Anybody?
So the first part's going to be sodium.
Sodium, very good.
Sodium.
And what's the next part? So you can look up CN in the table, right?
Yeah.
Okay.
And sorry, I'm looking for it.
Yeah, no problem, no problem. Take your time.
I'm having trouble finding it. What
It should
what
be
group is it in?
okay. It's not in a periodic table per se. Let me show you where you'll find it.
It's cyanide, right?
Cyanide, right. You'll find it in let me show you the table here. Where is my not there. Did I close it? Oh, here it is. Okay. So in this table, you would find it, you could find it on this page right here. Right? Cyanide, CN, right here. Or you would find it, let me turn this around. Or you should find it on this table. Where is it? Hold on. Or maybe it's not here. Oh, it's not here. Okay, so it's not on this page here, but I'm quite sure it's on the next page. Let's see here. Right, here it is. Cyanide. All right, so you can find it in, at least 2 pages in the table that I've posted. All right. Okay, so let's go back to the PowerPoint. So the name of this compound, choose the ink here. The name of this compound is sodium cyanide, which, by the way, is something that you would not want to drink. Not if you value your life. I mean, if you want to commit suicide, then go ahead. Okay. What about B? Okay, so how would you name B?
Is that magnesium perchlorate?
Magnesium perchlorate. You're absolutely right. Whoops. I hate when that happens. Okay, so that's, let me make sure that this is properly done. So perchlorate. All right. Okay, very good. All right, so that's how you name ionic compounds with polyatomic ions. Okay, now there's a group of compounds which I don't think you'd have met in your introductory chemistry course, known as hydrates. They're kind of unique because basically a hydrate is an ionic compound which has as a part of its structure a fixed number of water molecules associated with the formula unit of this compound, all right? So to name these compounds, basically what we do is name the ionic part pretty much in the same way as we have done before, but at the end, you have to indicate the number of water molecules. And again, you're going to use the prefixes that we met before, mono for 1, di for 2, tri for 3, and so on, all right? So let me just give you, I think I have an example. Before we move on to the example, another important thing, when it comes to writing down the formula of a hydrate, to indicate the water molecules present, we have to put a dot after the formula unit of the compound, right? And then we write down a coefficient representing the number of water molecules, like 2, 3, 4. If there's 1, then there's no coefficient needed. And that's it. So let me see if I have an example of that here. Okay, so here are 2 examples. So in the case of the first example, we have this hydrate here, BaCl2, then you have a dot, and then you have 2H2O, right? So the name of this compound would be barium chloride, which is the first part here. And then now to indicate the number of water molecules, we have to use a prefix di for 2, and then we end with hydrate. So the name of this compound is barium chloride dihydrate, all right? And then the next example here is CuSO4.5H2O. So the name of this compound is copper 2 sulfate pentahydrate. Pentahydrate because there are 5 water molecules associated with a formula unit of copper 2 sulfate. So that's basically how we name these compounds. And what you'll find is that hydrates are very interesting compounds because a couple of reasons why. For one, what you'll find is, well, before we mention what I was about to mention, let me also say that if you have, let's say, you know what, let me get out of this here and create another slide because I want to explain something in more detail and I need space to do that. So let me, okay, so let me go back to the barium chloride dihydrate. So BaCl2.2H2O, that's a formula for the hydrate, right? And okay, so we call this the hydrated form of this compound. And it turns out that you can easily remove the water by heating this compound to 100 degrees Celsius. So when that happens, you're going to end up with BaCl2 plus 2H2O, right? So as I said before, this form is called the hydrated form. And this form is called the anhydrous form. All right. And what you'll find also in some cases, well, in every case actually, is that the appearance of the hydrated form would be different from the appearance of the anhydrous form. Now, in the case of barium chloride dihydrate, this has a more crystalline appearance. All right. While the anhydrous form would be more of a powdery appearance. All right. But they're both white. They both have the same color, right? So there won't be a change in color in the case of the hydrated form of barium chloride when you heat it to form the anhydrous form. Both forms are white, but the appearance in terms of the hydrate being more crystalline appearing compared to the barium chloride, which would be more powdery in appearance. All right. Another thing I need to mention too is that this process can be easily reversed, right? So in other words, if you have the anhydrous form, you can simply add water to it and you're going to end up with the hydrated form, all right? So you can go back and forth between the hydrated and between the hydrated form and the anhydrous form. Now, let me also talk about another example. And the example I want to talk about here is CuSO4, all right? Pentahydrate, copper 2 sulfate pentahydrate. Again, you can easily remove the water by heating the hydrated form to the anhydrous form. However, in this case here, compared to what we just discussed, there will be a change in color because in the case of copper 2 sulfate, this has a blue color, all right? In the case of, and that's a hydrated form. So let me write hydrated here, all right? The hydrated form will be blue in color, but the anhydrous form will be white in color, right? So this is the anhydrous form, all right? And again, what we saw before in the case of barium chloride, you're going to see in the case of copper 2 sulfate in that the hydrated form will be more crystalline in appearance, while the anhydrous form will be more powdery, all right? So the point I'm getting at here is that in some cases, there won't be a color change when you heat the hydrated form to form the anhydrous form, right? However, the appearance will change in that the anhydrous form will be powdery, while the hydrated form will be crystalline. There are other cases where, in addition to the appearance being changed from crystalline to powdery, you will also have a color change. So in the case of copper 2 sulfate, the hydrated form is blue. When you heat it, you drive the water off, and the anhydrous form that results will have a white color, all right? So that's what happens in the case of hydrates. Okay, what time is it? Let me see here. Okay, so let's talk about, you know what? Let me see here. Okay, I'm not going to start with acids today because I want you to get some practice doing some problems. Now, what I'm going to do is I'm going to go to your Canvas page and I am going to publish okay, so I'm going to publish the assignments for chapter 2. And what I want you to do is go to Canvas right now and download it. And let me see here. And I want you to do some questions from it. You won't be able to do all of them because we're not finished with chapter 2, but I think it's important that you get into the habit of, oh Lord, what's going on here? You get into the habit of solving problems, answering questions, and so on. And you just spend the rest of the time today doing it. So this is, hold on 1 minute. Okay, so this is chapter 2 assignment, and you should be able to, based on what we have covered so far, do questions 1 through, let me see here. Okay, 1 through 17. All right. So of course you won't be able to do 1 through 17 right now, but I want you to at least get started. All right. So you can start with question number 1, and I'll just be here available to you if you encounter any difficulty, if you have any questions. concerning any of these problems. All right. So I want you to get started with these. And as far as the rest of the questions, well, we'll be able to finish chapter 2 next class, which will be Wednesday, and then you'll be able to do the rest of the questions. All right. So I want you to get started with question number 1. And if you have any questions, let me know.
Okay, thank you.
Mm-hmm.
Hey, Professor. Mr. Nicely.
Yes, sir.
Is it okay to leave the Zoom meeting?
I'm sorry?
Is it all right if I leave the Zoom meeting?
I guess so. I'm just hanging out here until 12:40.
12:40.
Just in case you guys have questions. Well, before you leave, let me just say that it might not be clear to you guys about how you would submit your assignments, right? So just to describe how you should do this. After completing your assignment, and I'm referring to chapter 1 assignment, which will be due on Wednesday. So the way you're going to submit it is that you can either scan it or you can take a picture. In either case, what you need to do is to save it as a PDF document. And then you're going to submit it in Canvas. And I think I've already created, let me check and make sure. I think I've created the portal for you to submit it. Let me just make sure that it is set up so that you can submit it. Okay, so you should be able to submit it in the Canvas portal. So you're going to go to assignments and then upload it there. All right, for assignment number 1. All right.
All right.
So that's basically how you're going to do it. Or if you prefer to turn it in person, that's fine by me as well. Like I think one of you is in my lab. So if you prefer to turn it into me during the lab period, that's fine.
Sure.
All right. So, those are the possible avenues you can take.
All right.
All right.
Sounds good.
All right. So if you're leaving now, I'll see you on Wednesday.
Wednesday. Okay. So the labs are only on Wednesday then.
No, the labs would be on Monday and Wednesdays. Hold on, let me check here. Yeah, the lab will be Mondays and Wednesdays at hold on. Hold on. Will be Monday and Wednesdays from 2 to 5:45.
2 to 5:45.
Right.
Okay.
So
then do we have a lab today?
Yes, we'll be meeting today. I'll discuss everything that that we'll be doing this semester.
Okay.
Mm-hmm. All
and
right.
That's, can you tell me what building and room that is?
It's in building 2, room 125, if I remember correctly.
Okay, that's on the first floor, yeah?
Yeah. Mm-hmm.
Okay. Building 2, room 125.
Yep.
Okay, sounds good.
Mm-hmm. All right.
All right, thank you.
All right, no problem.
All right, see you soon.
Mm-hmm.
Bye.
Am I free to leave too, Mr. Nicely?
Yeah, up to you really, because like I said, I'm just here to help if you have any problems.
Okay, and you said the last page of the syllabus, just take a picture of it, sign it, and submit it through Canvas on the app. Okay.
Yeah, Canvas. Email it to me as an attachment, PDF.
Okay.
All right.
All right. Have a good rest of your day.
Yeah, you too.